Close your eyes for a moment and imagine space not as an empty void, but as a fabric, an invisible mesh that can be folded, curved, even torn. This is space-time, the canvas upon which all reality is painted. And black holes are not, as the name might suggest, actual holes piercing this fabric. They are regions where space-time is so extremely curved, so intensely compressed, that it transforms into something almost beyond comprehension. The story of a black hole begins with stellar death. When a giant star, something with at least 20 times the mass of our Sun, burns through all its nuclear fuel, there is no more energy escaping from its core to counteract the relentless gravity trying to crush everything inward. And then, in a cosmic instant, the star collapses. Not gradually, but catastrophically. The core implodes, compressing all that mass into an ever smaller volume until something extraordinary happens. The collapse doesn't stop. All that mass, equivalent to dozens of suns, is compressed into such a small, dense region that gravity becomes absolute. And near this object, gravity is so strong that not even light, the fastest thing in the universe, can escape. Light that should travel in a straight line is bent, captured, pulled back into the abyss. That's why we call these objects black holes. Because they don't emit light, they are regions of absolute darkness against the starry backdrop of the cosmos. There is a boundary around every black hole, an invisible but absolute frontier. It's called the event horizon, not because you can see events happening there, but because it's the point of no return. If you cross that boundary, even traveling at the speed of light, you can never go back. There is no speed, no force, no conceivable technology that could rescue you. You would be inexorably pulled inward, toward the center, and at the heart of every black hole lies something that defies not only the imagination, but the very laws of physics, the singularity. It is a point of infinite density, where all the mass of the black hole is concentrated in an infinitesimally small space, perhaps without any dimension at all. At this point, Einstein's equations of general relativity collapse, mathematics produces infinities, and we don't really know what happens. The singularity is where our physics breaks down, where we enter truly unknown territory. Black holes are not static. They can grow, feed, and evolve. When matter, an unsuspecting star, clouds of gas, even entire planets, gets too close, it is drawn in and swallowed. And the black hole grows, becoming more massive, expanding its event horizon. Two black holes can even merge, their singularities combining in a catastrophic gravitational dance that releases more energy in seconds than all the stars in the observable universe emit in the same period. And, in theory, black holes can exist in all sizes. There could be micro-black holes the size of individual atoms, with incredibly concentrated mass but tiny event horizons. If they exist, they probably evaporate almost instantly through quantum processes. At the other extreme, there are truly colossal monsters. The largest known black hole has a mass equivalent to 40 billion suns. Try to visualize that. 40 billion stars like our Sun, all that mass concentrated in one region of space. Its event horizon would be larger than our entire solar system. It's a cosmic titan, a concentration of matter so vast that it defies any analogy. And these supermassive giants are not rare. They are found at the center of most large galaxies. Our own Milky Way has one, called Sagittarius A, with approximately 4 million times the mass of the Sun. It rests in the galactic core, around 26,000 light-years from us, an invisible but gravitationally dominant presence. Even though they are invisible by nature, emitting no light of their own, we can detect black holes by observing how they affect their environment. Stars orbiting close to something invisible, accelerating to incredible speeds, betraying the presence of enormous mass in a tiny space. Disks of superheated matter spiraling inward, shining intensely before crossing the event horizon and disappearing forever. And here's something surprising. Black holes can emit energy. Physicist Stephen Hawking theorized that due to quantum effects near the event horizon, black holes can slowly evaporate, emitting what we now call Hawking radiation. It's an incredibly slow process. A mountain-sized black hole would take trillions and trillions of years to evaporate completely. But the theory suggests that nothing is truly eternal, not even black holes. When a star gets too close to a black hole, something dramatically violent happens. The gravitational tidal forces, the difference in gravity between the side of the star closest to the black hole and the farthest side, become so extreme that the star is literally stretched, elongated like spaghetti in a process called, aptly, spaghettification. The star is torn apart, its materials forming a bright accretion disk before being swallowed up. Time behaves strangely near black holes. Due to gravitational time dilation predicted by general relativity, time passes more slowly in strong gravitational fields. To a distant observer, someone falling towards a black hole would appear to slow down asymptotically, never actually reaching the event horizon, eternally frozen on the threshold. But from the falling person's point of view, they would cross the horizon in finite time, noticing nothing special at the moment of passage. Speculative theories suggest that black holes may be more than just cosmic collectors of matter. They could be portals to other regions of space-time, perhaps even to entirely different universes. These ideas remain in the realm of theoretical speculation, but they capture the imagination. And some physicists have proposed even more radical ideas, that our own Big Bang, the birth of our universe, may have been the interior of a black hole in another universe. That perhaps universes are born inside black holes, creating a kind of nested and recursive multiverse. When two black holes collide and merge, the surrounding space-time is disturbed so violently that gravitational waves, ripples in the very fabric of space, are sent hurtling through the universe. And, remarkably, in 2015, we detected these waves for the first time on Earth, confirming yet another of Einstein's predictions and opening a new window to observe the cosmos. Breathe slowly. Feel the surprising stillness of concepts so extreme, so beyond everyday experience. For decades, black holes existed only in mathematics, in equations, in theory. We knew they should be there. We inferred their presence from the effects on nearby stars, but we had never seen them directly. Until 2019. In that year, a global collaboration of telescopes called the Event Horizon Telescope achieved something extraordinary. It captured the first real image of a black hole. The image showed the supermassive black hole at the center of the Messier 87 galaxy, about 55 million light-years away. And what we saw was both expected and surprising. A bright ring of reddish-orange light surrounding a perfectly black circular shadow. That shadow was the event horizon, the boundary beyond which not even light escapes, silhouetted against the glow of the surrounding material. The glow of that ring doesn't come from the black hole itself, but from matter swirling around it at speeds close to the speed of light. This material, gas, dust, perhaps remnants of shattered stars, forms an accretion disk around the black hole. As it spirals inward, friction and compression heat it to extreme temperatures, billions of degrees, causing it to shine intensely in X-rays and other radiation before crossing the event horizon and disappearing forever. And black holes aren't simply static spheres of gravity. They can rotate, and many rotate extremely fast, some at nearly the speed of light. A rotating black hole is called a Kerr black hole, named after the New Zealand physicist Roy Kerr, who first found the equations describing them. When a black hole spins, it does something even stranger. It drags space-time itself around it in a phenomenon called frame dragging. It's as if the space near the black hole is pulled along with the rotation, creating a region where it's impossible to remain still. You would be dragged along with the flow of space-time itself. There are also more exotic theoretical variations. The Reissner-Nordstrom black hole, for example, possesses electric charge in addition to mass and spin. In practice, real black holes probably don't retain significant electric charge for very long. Charged particles would be attracted to neutralize it. But mathematically, these solutions exist, exploring the limits of what is theoretically possible. The rotational speed of a black hole profoundly affects its properties. A rapidly spinning black hole has a different event horizon, flattened at the poles and bulging at the equator. And near rapidly rotating black holes, space-time drag becomes so extreme that it opens up strange possibilities, such as the ergosphere, a region where extracting rotational energy from the black hole would theoretically be possible. And black holes can be violently active in visible ways. Many launch colossal jets of plasma, superheated material, from their poles, shooting outward at speeds close to the speed of light. These jets can extend for thousands, even millions of light years, traversing entire galaxies. They are some of the most energetic phenomena in the universe, visible even across immense cosmological distances. Paradoxically, while black holes devour matter, these jets can seed surrounding regions with material that eventually collapses to form new stars. Destroyers and creators at the same time, shaping the evolution of the galaxies they inhabit. And the center of most large galaxies is profoundly shaped by the presence of a supermassive black hole. These gravitational titans, with masses of millions to billions of suns, influence galactic dynamics, regulating star formation through their jets and radiation, helping to sculpt the structure of galaxies over billions of years. But not all black holes are giants. Stellar black holes, born from the death of individual stars, are much smaller, typically only a few times the mass of the Sun. Their event horizon may be only a few kilometers in diameter, tiny compared to supermassive black holes whose horizons can be larger than solar systems. To create a stellar black hole, the progenitor star must be gigantic, at least about 20 times the mass of the Sun. Only stars on that scale have enough gravity to crush their core beyond the point of no return after burning their nuclear fuel. Our own Sun, despite all its brightness and heat, does not have this dramatic fate. If the Sun were to die today, and it eventually will in about 5 billion years, it is simply too small to collapse into a black hole. Instead, it will become a white dwarf, a dense but stable stellar corpse slowly cooling through the ages. Theoretically, primordial black holes, miniature black holes with masses perhaps as small as mountains, could have been created in the extreme conditions shortly after the Big Bang, when densities were astronomical and quantum fluctuations could collapse into singularities. If they exist, they could still be floating through the universe today, invisible and undetectable except for their gravitational effects. And there are even more exotic speculations. Some theoretical physicists propose that black holes may be connected by wormholes, tunnels through space-time linking distant regions of the universe, or perhaps even different universes. A black hole in one location could have an exit in a completely different place, like a cosmic shortcut. These ideas remain purely theoretical, probably impossible in practice, but mathematically fascinating, exploring the extreme limits of what equations allow. Let your mind wander through these dizzying concepts. Jets hurtling through galaxies, space-time being dragged along, tunnels connecting universes. Imagine for a moment that space-time is not just a screen on which events happen, but something with topology, with folds, curves, perhaps even shortcuts. Wormholes are these theoretical possibilities. Tunnels through the very fabric of space-time, connecting two distant places, perhaps separated by billions of light years, perhaps even in different universes, through a much shorter path. If they existed and were traversable, wormholes would allow something that seems to violate the fundamental limits of the universe, effectively faster than light travel. Not by violating the speed of light locally, but by bypassing the distance between 2 points, like folding a sheet of paper and piercing through the layers instead of traveling along the surface. And some scientists speculate that black holes could be entrances to these tunnels, that beyond the event horizon, perhaps there is not just an overwhelming singularity, but a passage to another place. It's pure theoretical speculation, probably impossible in reality, but mathematically fascinating. Returning to what we can observe, that accretion disk around black holes is one of the most energetic phenomena in the cosmos. Matter spirals inward, accelerating to relativistic speeds, being compressed and heated by friction and gravitational tidal forces. The faster it spins, the more energy is released. This radiant energy can be greater than that of a supernova, but released continuously for thousands or even millions of years. And black holes do make sound, not in the conventional sense. The vacuum of space doesn't transmit sound waves. But in galaxy clusters where there is hot, thin gas, supermassive black holes can create pressure waves, ripples that travel through this medium and are, technically, sound. NASA has recreated the sound of a black hole using pressure wave data from the hot gas in the Perseus cluster. The original sound is extremely low-pitched, so low that it completes a cycle every 10 million years, 67 octaves below middle C, infinitely lower than any human ear could detect. To make it audible, scientists increase the pitch millions of times, revealing a strange and haunting melody, like the deep hum of something ancient and immense. Black holes are not always active. When there is no matter nearby to consume, they can hibernate, existing quietly, invisibly, waiting. But they are eternal opportunists. If something approaches, a cloud of gas, an unsuspecting star, they awaken, capturing and devouring with renewed intensity. And here's a disturbing thought. It's possible we may have already passed close to a black hole without realizing it. If an isolated black hole, without a bright accretion disk, were to pass through the solar system at a safe distance, the curvature of space it would create might be too subtle to detect with our instruments. It would be a gravitational ghost, passing invisibly through the cosmic night. Black holes are not fixed in place. They can move through the galaxy as wandering objects, propelled by past gravitational interactions or ejected from binary systems when a companion star explodes. Some travel at millions of kilometers per hour, traversing the galaxy in solitary orbits. And then there are binary black holes, pairs of black holes orbiting each other in an increasingly tight gravitational dance. As they orbit, they emit gravitational waves, gradually losing energy, spiraling ever closer until they finally merge into a single, larger singularity. This merger is one of the most energetic events in the universe. In a fraction of a second, more energy is released in the form of gravitational waves than all the stars in the observable universe emit in the same period. Space-time itself trembles. Ripples propagate outward at the speed of light, traveling across billions of light years. And in September 2015, for the first time in history, we detected these waves. The LIGO detectors, incredibly sensitive laser interferometers, captured the ripples in space-time caused by two black holes merging more than 1 billion light-years away. It was a direct confirmation of yet another of Einstein's predictions, a century after he proposed the existence of gravitational waves. Since then, we have detected dozens of mergers, not just black holes, but also colliding neutron stars. Each detection gives us a window into cataclysmic events happening in distant corners of the universe, revealing populations of black holes that we could never have seen otherwise. Because black holes can be invisible even to the most advanced telescopes. If there is no nearby matter to form a bright accretion disk, if there are no companion stars to betray its presence gravitationally, an isolated black hole is perfectly dark against the black background of space. There could be millions of them floating around the galaxy, completely undetectable until something passes too close. It's a humbling reminder of how much we still don't know about the universe, of how many mysteries are still hidden in the darkness, waiting to be revealed. Let these thoughts float gently. Tunnels through space, gravitational symphonies, invisible abysses traversing the galaxy, an isolated black hole wandering through the vastness of intergalactic space can spend billions of years without consuming anything. It is patient on a scale that transcends any human conception of time. Floating through the void, invisible, waiting with the patience of eternity itself until something, by chance or fate, passes too close. And when a star has the misfortune of orbiting too close to a black hole, something brutal happens. The black hole begins to steal matter from the star like a cosmic vampire, pulling gas from its surface through its relentless gravity. This process can continue for millions of years, the star slowly being drained, until eventually nothing remains but a withered stellar corpse. Or, more dramatically, the star could be completely destroyed all at once. This is a tidal disruption event, when differential gravitational forces between the side of the star closest to the black hole and the far side become so extreme that the star is literally torn apart, spaghettified, and fragmented in a fraction of a second. A black hole can swallow an entire star in a few hours. The stellar material, now shattered, spirals inward into a temporary accretion disk, superheated by friction and compression, shining with extraordinary intensity in a final burst before crossing the event horizon and disappearing. Astronomers are able to detect these violent moments by observing sudden bursts of light and X-rays coming from galactic nuclei. A silent black hole suddenly flares brightly, announcing that it has just devoured a star. It's a rare event to witness, but when it happens, it provides valuable insights into black holes that would otherwise remain unseen. Some black holes have masses equivalent to hundreds of thousands, even hundreds of millions of suns. The largest are called ultramassive black holes, and they reside at the centers of the largest galaxies. We still don't fully understand how something so massive can form. There's a temporal problem. We observe supermassive black holes existing in a very young universe, only a few billion years after the Big Bang. How did they grow so large so quickly? One theory suggests they may have formed directly from the collapse of gigantic clouds of primordial gas, skipping the star stage entirely and being born already massive. Another theory proposes that smaller black holes merged repeatedly, growing through collisions and continuous feeding until they reached colossal masses. But this process takes time, perhaps longer than the young universe had. It is one of the unsolved puzzles of modern cosmology. Black holes don't just capture light, they can bend it. This phenomenon, called gravitational lensing, happens when the gravity of a massive object bends the path of light passing near it. For a black hole, the effect can be dramatic. A star behind the black hole might appear multiplied, distorted into arcs or rings, its image warped by the extreme curvature of space. This gravitational lens can help us find invisible black holes. If a black hole passes between us and a distant star, the star's light can be temporarily amplified and distorted, revealing the presence of the black hole even if it doesn't emit its own light. Einstein predicted these lensing effects over 100 years ago as a natural consequence of his theory of general relativity. As always, he was right. Today, gravitational lensing is a routine observational tool used to map mass distribution in the universe, including invisible dark matter. And time behaves in strange ways near black holes. If you could orbit close to a massive black hole, within the grip of its extreme gravity, but still outside the event horizon, you would experience something extraordinary: gravitational time dilation. For you, time would pass normally. But compared to distant observers, you would age much more slowly. Hours for you could be years or decades for people far from the black hole. It's a form of one-way time travel, moving forward into the future with no possibility of return. Black holes are the ultimate survivors. They can exist longer than any star in the universe. Stars are born, burn their fuel, and die. Galaxies evolve and merge. But black holes persist, growing slowly through accretion or fusion, but essentially eternal on human timescales. In the extremely distant future of the universe, we're talking googles of years, numbers with 100 zeros. After all the stars have died, all the galaxies have spread beyond the observable horizons. Almost only black holes will remain, floating through a dark and cold cosmos, evaporating very slowly through Hawking radiation until eventually, perhaps, even they disappear, leaving only floating quantum vacuum. And there's a provocative idea that some physicists are exploring, that black holes may store information about everything that has fallen into them. When matter crosses the event horizon, all information about its structure, history, composition, everything seems to be lost. But this would violate a fundamental principle of quantum physics, that information is never truly destroyed. Perhaps, in some way we don't yet understand, this information is preserved, encoded in the event horizon, or subtly emitted through Hawking radiation. It's called the black hole information paradox, and it remains one of the deepest unsolved problems in theoretical physics. Feel the vastness of these concepts. Cosmic vampires, gravitational lenses, one-way time travel, futures of eternal darkness. Relax even more deeply. We are approaching the final revelations about the abyss. Among all the mysteries that black holes present, perhaps none is as philosophically disturbing as the information paradox. In quantum mechanics, there is a fundamental principle. Information is never truly destroyed. You can scramble, encode, disperse, but information about the quantum state of a system always persists in some form. But what happens when something falls into a black hole? All information about that object, its atomic structure, its history, everything, seems to disappear beyond the event horizon, forever inaccessible. This dilemma has tormented physicists for decades, creating a seemingly irreconcilable tension between general relativity and quantum mechanics. Stephen Hawking, after years of pondering the problem, suggested that information might slowly escape through Hawking radiation. Those quantum particles that leak from the black hole over eons. Perhaps the radiation carries, subtly encoded, all the information that fell in. Not in an obvious way, but through complex quantum correlations. Other physicists believe that information never actually enters the black hole. It remains encoded, somehow imprinted on the event horizon itself, like data recorded on a disk. The interior of the black hole would then be a holographic projection of this surface information. This idea led to an even bolder theory, that black holes, and perhaps the entire universe, are fundamentally holographic. All the three-dimensional information of a volume of space can be encoded on its two-dimensional surface. It's an idea that sounds like science fiction, but it has rigorous mathematical foundations, suggesting that reality may have one less dimension than it appears. Some extreme mathematical simulations show that, under certain theoretical conditions, paths through black holes could go back in time. Closed temporal loops where you could, in principle, return to your own past. But these are mathematical curiosities, probably physically impossible. Nature seems to have mechanisms to prevent real temporal paradoxes. And here's something surreal about experiencing a black hole. If you crossed the event horizon, you wouldn't see sudden darkness. You would see light, distorted, warped, coming from all directions at once. The light from the entire outer universe would be compressed into an increasingly tight ring as you fell, while below you, toward the singularity, it would be darkness. It would be a visual experience impossible to adequately describe with words. And within the horizon, space and time would profoundly switch roles. Normally, you can move freely in space, but are inexorably dragged into the future in time. Inside a black hole, you could theoretically move in time, though only in one direction, but would inevitably be dragged in space, toward the singularity. Traveling to the center would be as inevitable as the passing of seconds is for us now. The singularity itself may be merely a mathematical artifact, not something physically real. When equations produce infinities, it usually means the theory is breaking down, not that infinities actually exist. The true nature of the center of a black hole likely requires a theory of quantum gravity, something we haven't fully developed yet. And there are provocative speculations that inside each black hole there may exist another entire universe. That when matter collapses beyond a certain point, instead of forming a singularity, it somehow rebounds, creating a new Big Bang in a space disconnected from our own. We could, in theory, be living inside a black hole in another universe and never know it. Despite being destructive, black holes are also creators. They can profoundly influence galaxy formation, acting as central engines that organize surrounding stars through their gravity. Their jets and radiation can regulate star formation, sculpting galactic structure over billions of years. And these relativistic jets that some black holes emit are of an almost incomprehensible power, carrying more energy than trillions of atomic bombs, sustained for millions of years, traversing entire galaxies. They are some of the most energetic phenomena in the known universe. But nothing is eternal, not even black holes. Through Hawking radiation, they evaporate very slowly. A stellar mass black hole would take more than 10⁶ years to evaporate completely, a number so vast that it makes the current age of the universe, a mere 13.8 billion years, seem like a blink of an eye. In the unimaginably distant future, when all black holes have finally evaporated, the universe will be almost devoid of usable energy. It will be a cold, dark, dispersed cosmos, heat death, maximum entropy, a nearly uniform sea of floating quantum particles with temperatures infinitesimally close to absolute zero. But some scientists speculate about possibilities even beyond that. Perhaps from the final collapse of a black hole, or through quantum fluctuations in an eternal vacuum, a new Big Bang could emerge. A new universe born from the ashes of the old, restarting the entire cycle. Universes being born and dying in eternal succession. A temporal multiverse where each cosmos eventually gives rise to the next. It's philosophical speculation as much as scientific. But it's a reminder that no matter how much we've learned about black holes, those objects that once existed only as mathematical curiosities, and now we know to be real, photographed, detected through their gravitational waves, they still hold profound mysteries. Now, take one last deep breath. Let your mind absorb this journey through the most extreme object in the universe. We journey from the birth of black holes in the collapse of dying stars, explore their event horizons where time and space bend to the extreme, and witness their singularities where known physics collapses. We saw the first real image of a black hole, a ring of fire surrounding absolute darkness. We heard its gravitational symphonies, waves in space-time itself detected across cosmological distances. We explored their varieties, stellar black holes, supermassive black holes, ultramassive black holes. Those that spin, dragging space-time along with them. Those that launch jets traversing galaxies. Those that wander alone through the void. We contemplate profound paradoxes, lost or encoded information, the holographic nature of reality, the possibility of universes being born inside black holes, one-way time travel through time dilation, and we glimpse distant futures, eras dominated by black holes after all the stars have died, slow evaporation through Hawking radiation, the final heat death of the cosmos, and perhaps rebirth in new Big Bangs. Black holes are more than just astronomical objects. They are natural laboratories where physics is pushed to extremes we could never replicate. They are frontiers between the known and the unknown, places where our best theories begin to break down. They remind us that the universe is stranger, more wonderful, more profoundly mysterious than any human imagination could conjure. That there are cosmic abysses where reality behaves in ways that defy intuition, where simple questions lead to profound paradoxes. And you, lying comfortably now, share the universe with these gravitational monsters. While you rest, they continue their eternal dance, spinning, devouring, evolving, shaping the cosmos around you through their relentless gravity. Sleep well. Dream of abysses that are not empty but full of mystery, of horizons beyond which no light returns, of the curvature of space-time itself. Good night.